Hello, my name is Dan Voicu and I am the creator of the G3S SAT solver algorithm. And today's presentation will be about the capabilities of G3S of running in parallel computing environment. And one more feature that my algorithm is capable of, but we'll talk about this a bit later. Now, to introduce the machine I am going to run the benchmarks today is it's an HPC EPIC 7513, and I have 4 processors available, physical processors with 32 cores each. Therefore, the logical processors you see here in number of 128 are mapped 101 with the physical ones. Now, the machine has been made available by Cluster Power, which is the largest data center in Eastern Europe. And Cluster Power is partnering with me in this particular project. The benchmark I will be using today is the Bartel. It's a Bartel suite. The Bartel suites are well known and specifically conceived to challenge various SAS solvers performances out there on the market. And the benchmark is built out of a number of conjunctive normal form files, and those files, those formula are split into batches of 5 based on their complexity. For instance, the top 5 are of complexity 200 variables in the number of clauses, and you'll see later on what this means. The next batch is 220 variables and a little bit more clauses, then 240 and so on, up to 540 variables per formula. Now, the complexity, as I said, is rising from batch to batch, but not linearly as the number of variables. So the difference from here to here is 20 variables. That means the complexity will grow exponentially. Why? Because the search space in a 200 variable formula is actually 2 power 200, being we're talking about Boolean variables. So 2 power 200 means roughly 10 to the 60, whereas the 10 to the 60 meaning what? Meaning that many combinations are available if any of those 10 to the 60 combinations represents a solution for that particular formula, then that one will be returned in case it is found in such a very large space, I would say. Now, the difference between this one and the next one, which is 2 power 220, which means 10 to 66, is over 1,000,000 times larger search space. Over 1,000,000 times larger search space, which is a big difference. Now, the algorithm will start running all the formula one by one and try to find the solution in the given search space of that particular formula in a, let's call it sequential manner, meaning that the algorithm will only use one core for the main run of G3 and a steady pool of 4 to 7 other cores for, let's call it, auxiliary tasks. So only one main core running, and the rest are auxiliary cores for different tasks. Whenever I will run in a parallel, it means that I will add extra cores for the main computation, right? But they will all share the same auxiliary pool. So let's start running G3S and apply it to all of the formula above. and see how it behaves. So far so good. It looks to me that everything runs smoothly, and I will explain you shortly what each column means. So let's see. This column here is about the file that, or the formula that's being solved currently. Then the number of variables contained in the formula, then the number of clauses for those formula. If a solution in the given search space is found, then the word satisfiable is printed out. I could print out also the solution itself, but it's gonna mess up with all the display here, and I'll do it later for one only. Now, the wall clock means exactly what it said, the raw time of the execution from start till a solution has been found. Now, let me wipe the board for a bit more clarity in terms of what the next column is or means. So the most important column is this one, where the order of complexity of the run is displayed, is being calculated by the algorithm. What does it mean? N means the number of variables in the formula. Power 3.08 here, it means the 280 variables to the 3.8. That is the considered complexity of that particular run. And as you can see, the complexity of the run goes from anywhere from 2.5 or so up to something larger, like 3 point something, 3.5 or so, like these ones. And that's in computer science and generally in non-deterministic polynomial complexity of a formula is considered as being a polynomial run, and sometimes is compared to the holy grail of this kind of satisfiability algorithm. So we're still looking polynomial in terms of runs complexity, and maybe we were just lucky, but we'll see that later on if this is luck or the algorithm is conceived to do exactly that no matter what, no matter the complexity of the formula, of the given formula. And right now we're at number 58 out of 70. And I know, since I ran this benchmark several times, that starting at 8:57, it will be done somewhere near 9:05 because it takes like 9:05, no, later than that, 9:10, 9:13, something like that, 9:13 a.m. because it takes around 1,000 seconds to finish the 70 formula. So in order not to hold you watching the scrolling screen, I will pause the video and come back by the end of the run. So see you later. So I'm back. The very last one is about to be solved, last of the formula in the benchmark. So so far it looks to me that the order of complexity held between somewhere between order of n to the 2.5 up to n to the order 3.5, order of n to the 3.5. So now that being said, you probably are wondering how I figure out, or the algorithm is figuring out, the order of complexity for a particular run. That's very simple. Actually, it's counting every single touch of a variable in the formula, and incrementing the number of touches, and then it's a simple logarithm based the number of variables is calculated, and that gives us the order of that particular run complexity. So so far, being in such a low polynomial order of complexity for the run is being considered as the holy grail in computer science and generally in the non-deterministic polynomial space, which is NP hard, NP complete, and NP generally, non-deterministic polynomial. And so far so good. It looks to me that either I'm lucky to be in this range, or G3S really behaves like that. Apparently, so far, it is like that in the low polynomial order, but we'll try to do better. Okay, the run is done, 1052 seconds. And now I'll explain a little bit about what it means to run in parallel for G3S. Remember the auxiliary pool that I showed you before? All right. And the main core that is running and using that auxiliary pool. In a parallel run, I will be adding more main cores, main logical processors. And one might think that as normal, a parallel run implies the concept of divide and conquer. Here is not the case. It's not the case because each of the cores will do exactly the same workload and will run exactly the same code as all the others. The only difference between this one and this one and this one and between the cores is actually the fact that they will start from a different point in the formula geometry. So having different starting points will return different results, and the fastest is being taken in as the final result. So that is about the parallel run. Now let me explain you a little bit about what you're about to see and witness. Next, I will be trying to box the complexity of the execution. What does it mean? It means that, for instance, this one here, which is being executed in order of n to the 3.31, or this one, it's even larger, I will be trying to box it at something less than that and force or ask G3S to do so. Let's to find a solution, a faster solution than the previous one. So I will be giving G3S 30 extra logical processors, and I will try to box its complexity for each individual formula to the order of n to the cube. You might wonder, how is this possible? Well, by its nature, G3S is built out of three different concepts. One is a simple logical mathematical concept, an extension of a well-known mathematical concept called the Gröbner basis. The other one is an AI module, and the third one is a genetic evolutionary algorithm that I use to implement G3S. Now let's see what the difference in complexity or in performance generally is between the previous run and this run, where the complexity is being boxed. Being boxed, it means that it's not necessarily able to find a solution within the order of the given order of complexity as a constraint, so namely n cube in this case. And as you can see, there is at least one that went beyond that order of complexity, and we'll take a look by the end of the run. We'll take a look at that particular formula and try to actually fix it and obtain a result before, faster than the one before. So right now it's at number 58, and let's see how long it's gonna take to finish and compare the performances between the two runs. So so far as I can tell, there is that only individual. No, there is another one here that went beyond the constraint I gave to my algorithm. But we've already reached number 66, and this looks to me that is quite an improvement in performance so far. And of course, given more horsepower, okay, so now that's done. And right now the algorithm is trying to clean up the mess behind using those extra cores. So the raw time is 92 seconds. Okay, let me break this cleanup and try to look at the difference in complexity or in performances. So 1052 seconds divided by, what was that? 92. Roughly 11 times faster, which is already some improvement. Now let's take a look at how many individual formula went beyond the imposed complexity. So that's one. So let's take this one, this single formula, and try to fix it. Try to find a way to obtain a better result, a faster solution for this formula. And we'll do that by giving it a little bit more extra power, but the same complexity box. Let's see how this happened. By the time it's taken, I would say it is not able to find a solution within the given complexity box with 40 cores. But we'll wait and see how it is going to behave in this particular run. And then we'll try to adjust the number of cores. Let's see how many it's using right now. That's roughly what I gave it, right? 35% of the 128 cores, and see if there is a better solution for this one. And then we'll try the rest. So far I'd say that it's not. And by the end of the run we'll try something different. Okay, no, it's not better. By contrary, it looks worse to me. So let's give it a little bit more of computation power. Okay, now that solved it. So basically with 50 cores, we could find a solution within a roughly n to the 2.6, which is already a big improvement. If you look at the number, it's under a second versus 60 seconds. Now that makes a big difference. A big difference. Why? Because clearly starting from a different number of points in the formula geometry, the algorithm could find a better solution. Now let's take a look at the other one, this one. And let's try to fix it. Okay, G3S, fix that. We'll try with 40. And then the complexity boxing to 3.0. Let's see how, okay, that went well. Much better than the other one. So we only needed 10 more from the previous run, 10 more cores in order to find a path that was faster than the one before. Now let's take the third one. I think it was right there. number 19, and try to fix it. Now G3S, help me please, and I'll give you 40 cores, and actually I will ask you to find a path, an execution path that will return a result before order of complexity of n to the cube. 3, we're getting closer. Okay, and that was with 40 points, and we're getting closer to what I wanted. Now let me give it a bit more horsepower, because I'm not really content with the result, and it's getting better. Okay, very close to what I asked for. And let me give it a bit more. See whether it's able. Yep. Oh, it's not better. Let me try a bit more. I still want. I'm still very stubborn and ask my algorithm to find something that's faster. And yeah, we're getting closer. The point is that a formula may have no solution, or one solution, or several solutions. Depending on the starting point in the algorithm, the one or many solutions may be found in different ways. Therefore, whatever I gave it as a number of main cores to execute, they will all start from a different point in the formula. So we're just very close to 3.0, so I'll be just leave it as is and consider it as a victory, because 3.01 is in the range of n cube, very close to that. Now again, since the algorithm is using 3 main concepts, you might wonder, what are the performances is this capable of? And in my next recording and the videos, you will see something that is being very particular to this algorithm. Namely, I'll ask G3S to find all the solutions in a search space, which is something that I never heard of any algorithm being able to do an exhaustive search on such a large space. And let's not forget the size of the space, at least for the biggest formula out in the benchmark here, is 2 power 540, meaning 10 to the 162. It's a very large space, but G3S is capable of finding solution in much larger spaces than this. And just to have an idea how such a result looks like, let's try the last one, and let it display the solution. Okay, and the solution looks like this. Basically, this is variable number 1 with positive polarity, basically means true. Number 2, number 3, number 4, and number 6 here that shows a negative polarity, so the Boolean is set to false. As I said, in my next video, you will be witnessing the exhaustive search in a given search space, which is quite particular for this algorithm. That being said, I will finish my recording and start my next one very soon, and talk to you then. Bye bye.